Hello everyone. In this video we are going to understand what is the stress. It's not a big deal to understand what is the stress, but the usual definition for stress is it is the internal resistance that is offered by a body against deformation. So that is the usual definition for stress. Mathematically speaking, people also say that stress is load over area. Okay, now in this video what I will try to do is I will try to give you an intuitive understanding of what a stress actually is. And we are also going to understand the concept of stress mathematically as we delve deeper into the subject matter. Now to begin with, let me do a tensile test experiment. You know what is a tensile test experiment? You actually take a rod, you can call this a bar, it's a rod, and you actually pull this rod on either side. So that's the tensile test experiment. We are going to do this tensile test experiment on two materials. The first material is steel, and this yellow guy, that will be, let us say that it is a material that is not as strong as compared to steel. Let us say that it is aluminum. Okay, the first material, that is steel. Now we are going to do a tensile test experiment, which means you pull the rod, that's right. So for obvious reasons, you know very well that steel is strong compared to aluminum. So steel is not going to break first. So you know that this guy is going to win. Steel is going to win. So steel is stronger compared to aluminum. Simple as that. Now, when I did this experiment, I made a simple assumption. That assumption is the cross-sectional area of these two materials are assumed to be the same. And also, please note that when I say that there is a load that is acting here, understand that this load is actually spread over the entire cross-sectional area. So this load is not acting on one particular point. As indicated, it's not acting on one particular point. The resultant of all these forces will be acting on a particular point. That is what is mentioned here. So in actual physical scenario, the resultant, the load is actually spread over the entire cross-sectional area. It is distributed throughout the entire cross-sectional area. And for all practicable purposes, now just for conducive reasons, what I'm actually doing is I'm just representing the load to be a point load. That's it. So hope that is very clear. Now I'm going to do a second experiment. This is case 2. So this is case 1, and case 2 I'm going to do this same experiment, but this time I'm going to take a steel rod, and what I'm actually going to do is I'm going to increase the cross-sectional area of aluminum. Right? So I have increased the cross-sectional area of aluminum. So that is aluminum. The first one, and here it is steel. Now this time I'm going to do the same tensile test experiment. Now aluminum behaves as if it is strong compared to steel. So you know that aluminum behaves in the second case. It behaves as if it is very strong compared to steel. Now what is the reason for that? Well, whether a material, how strong it is, at least the way it behaves, depends not only on the load, but it also depends on the cross-sectional area. So that's the reason why we are saying that the stress that is produced on these materials. So let us say that these materials are conscious. If you assume that these materials are conscious beings, then they will say, obviously they are going to say, well, I am experiencing stress. They are going to say that. Well, the amount of the magnitude of stress that is experienced by these conscious beings, let me make sure that these are actually conscious beings. If the stress that is experienced by these materials, these conscious beings, what will they say? Well, if the load, I'm sorry, not the load, if the load may be greater, But if the cross-sectional area is also greater, then the materials will be very happy because they are not going to experience much of a stress. They are very happy. On the other hand, if the load is greater, but on the other hand, the cross-sectional area is not that high, then we can say that the stress that is produced on this material will be very high. So this guy is not going to be very happy. So he is not going to be very happy. The reason is because he is experiencing more stress. So clearly, the stress experienced by these conscious beings, assuming that they are conscious, is directly proportional to the force, and it is inversely proportional to the cross-sectional area. So the unit for force is Newton, and the unit for area is either it is meter square or mm square. Usually in the textbook they use mm square, so it's Newton per mm square. That's right. Now, having defined the concept of stress, when the stress value in a particular material reaches a permissible limit, then the material is going to break. Irrespective of its geometry, if the stress value in a particular material reaches its permissible limit, then the material will fail. So that in that way we can start drawing the stress strain curve, but that's for another video. Okay, so let us recapitulate the concept. So what is stress? People say that it's the internal resistance offered by a body against deformation. Stress is load over area. Well, you have two guys, one is steel, another one is aluminum, and which one is going to break first? For obvious reasons, if both the materials have the same cross-sectional area, aluminum is going to break first. And they are going to experience the same stress, but aluminum is weak. So for the same values of stress, aluminum is not so strong, so it's going to break. The second case, you are just going to increase the cross-sectional area of aluminum. This time, aluminum is not experiencing that much stress. Let us say that, for example, in the first case, let us say that this guy, let us assume that he breaks at 100 units of stress. So I'm not saying Newton per mm square. I don't remember the exact value of stress at which aluminum is going to fail. So let us assume that he is going to fail at 100. Here, this fat guy, when this value of stress reaches 100 for this fat guy, he will fail. So irrespective of the cross-sectional area, the value of stress at which a particular material is going to fail, it always remains the same. Okay, good. So that's the definition for stress. That's a bit of an understanding for stress. Okay, here is an example. You take a sharp pencil, so that's going to break that easily. The reason why it breaks easily is because the cross-sectional area is low, so the pencil is going to experience more stress because stress is load over area. On the other hand, you take a blunt pencil, it's not going to break that easily. The reason why it's not going to break that easily because you have a greater cross-sectional area, so it's not going to break that easily. A few more examples here. You see the radial tire of your car, it's flat. They are increasing the cross-sectional area so that the weight is distributed in that region, so that you are actually increasing the longevity of the tire. And you can see that here is the picture of MacBook. There is a fillet that is provided. So in case if the laptop falls down, so it's not going to, the edges will not break that easily because you have increased the cross-sectional area. Thereby you are going to reduce the magnitude of stress. Here there is another example, and this is iPhone, and you can see that the edges are rounded off so that you increase the cross-sectional area. And what about you carrying a carry bag? In India, for example, there is a carry bag, and if you put a lot of weight, then of course you are going to experience a lot of stress. To increase the cross-sectional area, you take your handkerchief, you use your handkerchief. That way you are actually going to use, you are increasing the cross-sectional area, so you experience low stress. So these are some of the intuitive examples for stress. So whether your material is going to break or not depends not only on load, but it also depends on the cross-sectional area. However, if the magnitude of stress reaches a permissible value in a given material, the material will always fail. Okay? So stress clearly is a material property. It's not a geometric property. It is a material property. Because no matter what the cross-sectional area of aluminum is, this can be 10 cross-section, this can be of 500 in cross-section, and this can be of 1000 in cross-section. If this material has to break at 100, if the magnitude of stress reaches 100 in this material, it breaks. If the magnitude of stress reaches in this material, it breaks. If the magnitude of stress reaches 100 in the third case, it also breaks. So stress, clearly it is a material property irrespective of the geometry. When the magnitude of stress reaches a permissible value, the material will fail. Goes beyond the permissible value, the material is going to fail. Thank you all for your patience. Thank you so much.